Hello everybody. So now let us continue discussion further on anion binding. So in the previous lecture, we looked at the role of pH in being able to influence the binding of different species with a given host. So we looked at the soccer ball complex, where the change in the pH can actually influence the binding of either a cationic species, a neutral species and an anionic species, depending upon whether the host is neutral, partially protonated or completely protonated. Now we will look at the next factor which influences the selectivity of anions, and that is by the shape complementarity. So the shape selectivity is something we would now to explore here, and in order to look at this particular shape selectivity, we will now consider the following ligand, which is drawn as follows. And so this is referred to as a complex. So this particular complex, we are going to now protonate the hydrogens, the nitrogens here. This we call as the H6 tren 6 plus complex. So you can see this is a hexacationic host, and it has got a large cavity associated with it, and this cavity can now include different kind of anions. So in this particular so this cavity, as you can see, is cylindrical in nature, and you can view it from here or you can view it from here. It essentially resembles a cylinder, and we can now have different kind of anions. For example, we can first start with the halides: fluoride, chloride, bromide and iodide. The magnitude of the equilibrium constant is given, that is 4.19, 3.0, 2.6 and 2.15, and the log K value is 4.30 for the azide ion. And the position of all the atoms in the anion bound complex has been determined by X-ray crystallography. So X-ray crystal structures have been determined for all the anionic complexes which are bound with this particular H6 tren complex. And what has been observed is the following, that when you look at the fluoride anion is the one which has got the highest charge density. So in the case of fluoride, it is positioned somewhere here. this is the position of fluoride, whereas in the case of chloride it is positioned more at the center. In the case of bromide also it is more or less positioned in the vicinity of the chloride. So, bromide and iodide being larger in size are able to get accommodated more towards the center of the cavity, whereas the fluoride is more towards one side. That means there is unsymmetrical binding or bonding in case of fluoride. Now, in case of fluoride we have got strong NH plus F minus hydrogen bonds. These are the charge assisted. These are the charge assisted hydrogen bonds, and the distance between N and F minus, that means the donor atom and the acceptor atom, is 2.72 angstrom. And all these distances you can now get by careful inspection of the crystal structure. In the case of chloride it is around 3.2 to 3.4 angstrom. In the case of bromide it is around 3.3 to 3.5, 3.3 to 3.5 angstrom. So, now what is more interesting to observe that in this particular case, that it is fluoride which is the most extensively solvated, but it is also the fluoride which has got the highest value of the binding constant. So, the magnitude of the binding constant follows the order of solvation. In fact, it is a surprising result, because if solvation is more, then more energy has to be spent in solvation to enhance the binding. But essentially what drives the system is the larger number of enthalpically favorable NH-F minus hydrogen bonds that drive the association process. The strength of the hydrogen bond decreases when the electronegativity drops to chloride, bromide and iodide, thereby indicating a reduced binding constant. What was more interesting is that in the case of the azide now, if you now look at the azide, so I will now remove these ions which are present here. If you now look at the azide, then the azide is positioned symmetrically. The azide is positioned symmetrically such that it interacts with these hydrogen bonds, it interacts with these hydrogen bonds, it interacts with these hydrogen bonds, and it can interact with these hydrogen bonds. So, in the case of azide, there is the formation of N plus, there is a formation of NH plus N minus hydrogen bonds. And also the magnitude of the binding constant is highest in case of azide, because it indicates a nice steric fit. So, the shape of the azide ion is that it is linear, and it very nicely fits into the cylindrical cavity which is created by the hexatren host. So, the cationic host has got a cavity, and the cavity, this particular void is more of a cylindrical cavity, and this linear azide molecule is able to very nicely sterically fit into this particular cavity, thereby engaging in strong NHN hydrogen bonds, and that is reflected in the large magnitude of the binding constant. So, this is what is very interesting, that when you have got, so the factors that drive anion binding here, that drive anion binding, in this case we saw in case of fluoride it is the size small and high charge. In the case of azide it is both the topological shape and the charge distribution. So, both these factors play an important role. That means the size, here it is the shape in the case of azide, and the charge distribution. And so, overall we will see that electrostatics provide the driving force. And this is enhanced by increase, the electrostatic forces are enhanced by increase in number of hydrogen bonding interactions. So, these are the factors which get reflected in the enhanced binding of azide in this particular hexatetrane complex. Now, what was also done is that in order to improve the binding with the fluoride, in order to enhance binding with fluoride, a slightly modified gas was taken. A slightly modified gas was taken. A slightly modified gas was taken, where we have, if you compare now between this, so we have now removed this particular part. This particular part has been chipped off. This particular part has been removed, and now we have got a slightly modified host, and in this host we have again hexaprotonated it. And the fluoride can now come and sit in the center and form NH plus F minus hydrogen bonds. And after looking carefully at the crystal structure, it was observed that the NF minus distances are 2.76 to 8.6 angstrom, and the magnitude of the log K is 11.2, and you have got more symmetrical binding. So, chemists can make fascinating molecules. The chemists can modify the substrate in a way that they can actually now allow for enhanced fluoride binding in a slightly modified hexacationic host, where the side chain has been truncated, and the fluoride is now able to participate in the same set of hydrogen bonds, and because you have now truncated the side chain, the cavity size also reduces, and fluoride is having a small size. So, that allows for a nice steric fit and fluoride to be included in the crystal structure. So, these kind of features have been observed, which talk about the relevance of shape selectivity in governing anion bonding. The next most important complex we would like to take, the next important set of complexes which are also of relevance in understanding biological anion receptors, that means proteins which are sensitive to anions, and another very important receptor is the arginine residues. So, now this the arginine residues which contain the guanidinium units. Now, in case of the guanidinium, we can see that the guanidinium unit is present on the arginine residue. Let us draw red structures. For example, we can see here, this is my guanidine, and it is actually appended on the arginine residue. So, this is my the arginine, and now we have got the protonation of this. So, protonation of this makes it NH2 plus, and now we can have different receptors which can form hydrogen bonds forming NHO minus hydrogen bonds with acetates. Okay. So, this becomes a very interesting binding motif where the acetates are being sensed by the guanidinium cation. Now, what is the property of guanidinium is as follows. It is as follows. Guanidinium, that is the protonated form, it is an excellent anion binding site because it remains protonated over a wide range of pH. So, the pK is 13.5 for the species CN3H6 plus, that is C, NH2, NH2 and NH2, this is carbon. So, this is the protonated form of guanidine, and you can see that the pK of this is 13.5, and therefore, its Bronsted acidity is very low, and therefore, it will not like to release the proton so very easily. And because it is stable over a wide range of pH, that means till pK 13.5, the other anions with which it binds also exist in this pH range. For example, we would like to look at phosphates, or we would like to look at HPO4 minus or H2PO4 minus. If we are looking at these kind of anions, then we will see that they all have got negative charges, and these negative charges will essentially interact with the cationic host, and the phosphate will also exist in the same range of pH in which the guanidinium moieties exist. So, that is why they got this very important property that they exist at the same conditions, same basic conditions at which the phosphate moiety exist. Now, this is very interesting because what has been isolated is the methyl guanidinium cation. So, have the methyl this is methyl guanidinium cation, and it is stabilized by this is H2PO4 minus. Okay, this is my phosphate ion. So, there is strong hydrogen bonding, that is N plus HO minus and NHO. So, you have these strong hydrogen bonds in the solid state. So, they are responsible for the strong affinity of the guanidinium moiety with the phosphate moiety, and there is a strong stabilization, a strong energetic stabilization because of these hydrogen bonds which exist between the species. So, but what is observed is that when this thing was observed, that now we have got strong affinity and this energetic stabilization, people started designing different kind of receptors or hosts to sense phosphate anion. And in this regard, first two important hosts were designed. Let me draw the structures of those two hosts. These are slightly larger structures. Please bear with me. So these are my 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is my one particular host. I've got a specific host, and then some other. So this has the positive charge here. This is the positive charge here. This is the positive charge. So this has got the threefold symmetry. So this is one particular host which was designed, and this is a cationic host which can sense the phosphate anion, and another host was designed where so 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. And then we have the positive charge here, we have got the positive charge here. So this is the host B. So both these hosts were actually synthesized, designed, and as you can see, there is a lot of hydrophobic content in this, but they also have got a lot of polar content. They have got threefold symmetry, but surprisingly, the value of log K was 2.4 for this, and log K was only 1.7. So this experiment completely failed because these large, we had till now we had assumed that in order to have good binding, the size of the host should be larger, and the anion should be able to sit in the voids which is created by the cationic host. But in this particular case, these experiments did not work. So one possible reason is that the phosphate is too small to fit into the cavity, and number two, this is a rigid host. It is rigid because it wants to maintain the delocalization at the guanidinium moieties, so that makes it quite rigid. So this particular host is quite a rigid host because it has to maintain the planarity to maintain the delocalization. And the third thing is that extensive solvation of the host itself. So in the previous case we saw, although the anion which is the guest can be solvated, but yet it tends to get included in the structure. In this case now the host tends to get highly solvated, and because it is highly solvated, it is not able to participate extensively in anion binding. So that becomes a limitation of sorts, and in order to improve this particular process, much more research went on in this guanidinium based cationic moieties, and then some modifications were proposed which actually led to enhanced binding in case of guanidinium moieties. So what was the modification which was proposed? So the following substrate was then designed. So now you can see chemists can make fascinating molecules. They can modify the templates. So you now see this is a very modified guanidinium, modified guanidinium host. And now you see there is a reduction in the positivity. So it is only positive in this particular region, but it also has got enhanced lipophilicity. So when you have got reduced positive charge and you have got enhanced lipophilicity, then the extensive solvation will not take place. That will minimize the solvation, and therefore this kind of host is expected to have much stronger binding with the phosphate anion. This work was done by a scientist called Smith Chen in 1980, and as we can see that you have reduced the resolvation because you have reduced the hydrophilic core and you have enhanced the lipophilicity. So, now the binding with para-nitro benzoate anion, and you know we have already looked at this fact that now you have got benzoate anion. So, it can interact with NH via these hydrogen bonds, and when it will interact, the magnitude of the equilibrium constant now becomes 1.4 into 10 to the power 5 molar inverse in chloroform. So, when these experiments were done in chloroform and in the presence of para-nitrobenzoate, the magnitude of the binding constant becomes very high. So, modified guanidinium host can now actually enhance these kind of processes. Another particular host was also designed which modifies this binding with the anion, particularly the phosphate based anions. And why phosphate based anions are important? Because they have a lot of applications in biological systems. For example, we look at little at enzyme mimics, and phosphates and other derivatives of phosphates like oligophosphates are very important in the biological system. So, we can now take another modified host. For example, we can take this one now. This is plus here, this is plus, this is CO, this is NH, NH2 plus, NH2. Now, here we have got very cooperative bonding, because you will have this side the guanidinium moiety, this side also you have the guanidine, and they can interact with the phosphate. They can interact with the phosphate, and what has been observed is the magnitude of the equilibrium constant now is 5 into 10 to the power 4 molar inverse in acetonitrile. So, this is the magnitude of the binding constant when you have the corresponding RO2POO minus, and this also function as a supramolecular catalyst, because if you now want to do a trans-esterification reaction, if you want to do a trans-esterification reaction where you replace R with some R prime, then the rate for that particular reaction is 300-fold enhanced in comparison to that of the uncatalyzed reaction. This is the enhancement in the rate. So, when you want to do the trans-esterification reaction using this particular phosphate, replace OR with OR prime, then that reaction proceeds 300-fold faster in the presence of this particular supramolecular catalyst, that is the guanidinium based moiety, which is strongly hydrogen bonded with the phosphate, and this strong hydrogen bond actually lowers the activation energy necessary for the esterification process and achieves faster reaction rates. So, keeping these things in mind, we have now seen that you can actually have modified guanidine residues which can actually modulate the anion binding characteristics. The last example which I would like to discuss is you can also use hydride sponge combined with Lewis acid chelates to complex anions. This is another very versatile approach which has been adopted. For example, let us look at this case where we have NMe2 and NMe2. There is a lot of electron density here, and now we add in a proton. And what does the proton do? The proton now goes and Okay, so we have got these proton. Now the proton is essentially the positive charge here, and it also interacts with this lone pair. So we have this delocalized system, and we call this resonance assisted NHN plus hydrogen bond. So the proton is definitely very stabilized in this particular arrangement. On the same lines, we can now actually have Lewis acidic sites BMe2 boron based Lewis acidic sites, and now we add in a hydride ion, and the source of hydride ion comes from BH minus ET3. So triethyl borohydride, and it will interact strongly with the boron center here and form so it will form this hydride bridge. Okay, and the interaction energy is approximately 70 kilojoule per mole. And that means the hydride ion, it interacts strongly with the boron center, and this negative charge can now be delocalized over the two boron centers, and therefore we can now have this. So effectively this electron deficient complex, the boron complex, functions as a hydride sponge in that it can absorb hydride ion and forms the tetrahedral complexes, whereby the anions, the hydride ions, can be effectively captured in this process. So hydride sponge also is a very interesting mechanism when it comes to sequestration of anions. Now in the next lecture we will now go on to other types of applications of anions. We will now look at biological anion receptors and some applications of ion transports, particularly cationic ion transport as well as anionic transports, anion ion transports in structural biology. Thank you.